Welcome to today's explainer. Okay, I want you to do me a favor. Just close your eyes for a quick second and imagine standing right at the edge of a rabbit hole. But instead of tree roots and dirt, this rabbit hole is made entirely of crisp lines and perfect angles. Today, we're going to explore a very specific kind of mathematical magic. We're going to see how one incredibly simple geometric rule, repeated over and over again, can create mesmerizing, complex art. All right, open your eyes because we are heading straight down the geometric rabbit hole.
So here is the big question that's going to guide our entire journey today. What happens when you take a plain, kind of boring, everyday shape and you just twist it forever? I mean, for anyone who's ever doodled in the margins of a notebook, you know that repeating a simple pattern can sometimes get wildly out of hand. Well, today we are going to actually harness that endless repetition. Imagine falling down a tunnel of repeating shapes that spin and shrink into infinity. Let's find out exactly what that looks like.
Chapter 1. Meet the regular polygons. Before the real magic happens, we need to set the stage by introducing some familiar friends, right before they completely twist away from us.
Think about a simple three-sided triangle spiral. What do you notice about its three sides? At the very outer edge, it's just a normal flat triangle. But as you draw your focus to the center, you see how those inner lines start to play tricks on your eyes? It literally looks like the flat shape is suddenly scooping inward, creating three distinct sweeping curves that dive right into the middle.
Now, let's upgrade to four sides, a square spiral. Can you trace the paths with your eyes? Try counting the number of twisting paths diving into the middle. You'll notice there are exactly four winding trails, perfectly matching the four straight sides of the original square on the outside. It's like a square tunnel spinning completely away from us into the distance.
Let's keep adding sides, a five-sided pentagon. With five sides, this really starts to look like a magical swirling vortex. The straight lines are still there. Actually, if you look really closely, every single piece of this structure is perfectly straight. Yet somehow, your brain sees these beautiful, sweeping, curved spiral paths carrying you all the way down to a tiny point in the middle.
And this brilliantly illustrates what happens when we jump to six sides. A six-sided hexagon creates an even more intricate inward pattern. The more sides we add to our starting shape, well, the tighter and more delicate the vortex becomes. But underneath all of these swirling illusions, there is a very strict, unbreakable mathematical foundation.
So, the crucial point is that all of these starting shapes belong to a specific mathematical family. They are all what we call regular polygons. A regular polygon is simply a closed shape where every side is the exact same length and every inside angle is exactly the same size. Perfect, uniform, and totally balanced. That perfect balance is what allows our magical twist to work so beautifully later on.
Chapter 2. The Shrink and Twist. Okay, let's dive into this. How are we actually making these vortex illusions? What is the actual mechanical rule that acts as our magical shrinking potion? It turns out you don't even need a computer to do this.
Let's walk through the steps nice and slow. Step 1. You pick a ratio, which is just a specific distance along a side, say, exactly 80% of the way down. Step 2. You draw a new point right there, and you do this for every single side of your shape. Step 3. You connect those new dots. Because you move slightly down the line, this new shape inside is going to be a little bit smaller, and it will be slightly turned. Step 4. You literally just repeat the entire process on the new, smaller shape. We just put a smaller shape inside and turn it a little bit. That's the whole secret.
Now, there is a very important vocabulary word for this repetitive shrink and twist potion we just applied. It's called an iteration. An iteration is simply one repetition of the same construction rule. So every single time we draw a new, smaller, twisted polygon inside the last one, we are completing one iteration. Do enough iterations, and boom, you fall right down the rabbit hole.
Chapter 3. Down the geometric spiral. Let's move on and see how this builds. We know the shapes, and we know the rule. Now it's time to really observe the visual payoff of what happens when we let this process run over and over again.
When we observe this simple geometric rule creating such a complex visual pattern, I want you to do a quick notice and wonder with me. Take a few seconds. What appears to be moving? What appears to shrink? And what appears to stay exactly the same as we fall toward the center? You might notice that the overall shape shrinks and rotates with every step, but the number of corners always stays exactly the same. 5 sides on the outside, 5 sides on the very smallest inside shape.
You are also probably noticing those smooth curves again. This brings us to our definition of a spiral, a path that winds around a center while moving inward or outward. Even though we are only drawing straight-sided polygons, if you trace how one specific corner moves from the biggest shape to the next, through time, that imaginary path creates a perfect, smooth curve known as a logarithmic spiral. Why logarithmic? Well, because these regular polygons are equiangular, meaning all their angles are equal, the distance between the turns gets proportionally smaller and smaller as it twists closer to the center. It creates that beautiful, seashell-like curve.
What makes this geometric trick absolutely fascinating is grounding the magic in what doesn't change. In math, we call these unchangeable things invariants. No matter how deep down the rabbit hole we go, these rules never break. Every new polygon has the exact same number of sides. Every new corner or vertex sits perfectly on the straight edge of the polygon that came before it. And crucially, every new polygon remains perfectly regular. All its sides and angles stay perfectly equal no matter how tiny they get.
Chapter 4. The Math Behind the Magic. We've seen the beautiful results, but now I want to briefly reveal the secret logic that makes this geometric wonderland possible. Don't worry, we aren't going to get bogged down in heavy calculations, but looking at the blueprint is honestly pretty cool.
Now, what's really interesting about this mathematical blueprint is the formula. B sub I equals 1 minus R times A sub I plus R times A sub I plus 1. Okay, I know, that sounds like total alphabet soup, but let's decode it simply. The A's just represent the two corners of the side you're working on. The B is the brand new point you are drawing. This equation is literally just the mathematical way of saying, start at one corner, slide a specific percentage of the way down the line, and draw a dot. That's the whole shebang.
And the undisputed star of that equation is the letter R, which stands for ratio. The ratio is just a magical instruction telling the shape exactly how much to shrink and twist. If your ratio is 0.80, you are telling the computer, or your pencil, to travel exactly 80% down the line before making the next corner. Changing that single ratio totally changes how tight the spiral winds. A tiny ratio might plunge straight into the center almost instantly, while a larger one takes its time, gently swirling down.
Chapter 5. Playful Math Art. For our final chapter, let's step completely out of the mathematical rabbit hole and into the physical world. What does all of this look like when we take it off the screen or the graph paper and bring it into 3 dimensions?
Bringing this into reality with colorful 3D printed nested polygons is a real game changer. If you compare physical models, you can clearly see the differences in depth, the literal physical layers stacked on top of one another, and of course, the different number of sides. By turning the lines into physical walls, the twist and shrink effect creates these amazing colorful bowls that you can actually hold in your hands. You really see this come to life in a bold blue and white 3D printed spiral. By alternating the colors, the physical layers of a pentagon perfectly show the continuous inward winding of the iterations. You can literally trace that logarithmic spiral with your finger, stepping down layer by layer, twisting toward the very center. It's math that you can actually touch and feel.
And observing a whole collection of these nested shapes, squares, pentagons, different ratios creating entirely different depths and twists is just incredible. It perfectly shows how repeating one incredibly simple action, just drawing a point a little further down a line, creates mesmerizing, touchable math.
So I want to leave you with one final provocative thought. We started with a 3-sided triangle, right? Then a 4-sided square, then 5 and 6. The curves got smoother and tighter. So, what happens if our starting shape has infinite sides? What happens when a regular polygon essentially becomes a perfect circle and we try to apply our shrink and twist rule to it? Let your imagination spin on that one. Thank you for falling down the geometric rabbit hole with me in today's explainer. Keep wondering and keep exploring.